All right, let's go ahead and jump back in, pick up where we left off. So we were working through a bunch of these balancing problems, and I want to work a couple more of the. So I'm not gonna work out all of them because we could save some and do them on Thursday. Because I did post the actual, just the balancing, nothing else. I posted that to Blackboard. So we'll work on. I'm gonna edit that sheet though, and add some more problems to it. But we'll work on that work on that some more on Thursday. But let's take a couple of more because you can't ever get enough practice with balancing. Let's take these two. I'm gonna cut them out and put them on a blank sheet so we can have room to work. Even though that was the purpose of putting space between them. Let's see. Oh, wrong image. Did I not copy that? It's coming. It's Monday. Move that down. So, all right, let's take the top one. And again, this is one where I kind of talked about on Friday. It's kind of a nuanced, like way to balance, which is to leave the polyatomics intact, right? Because you can see the sulfate is on both sides. It's not broken up. It's not apart. And then the NO2 is also on both sides. It hasn't changed. So we could actually leave those together and balance it that way. I like to do it that way because it's less cumbersome because you don't have to list every atom. You can just list the polyatomics like whole and not have to break them up into their constituents. So let's see, on this side, we have two hydrogens. All right, we got two hydrogens. We have one sodium. We have, excuse me, one SO4 and one NO2. All right. So now on the other side, we have one hydrogen, two sodiums, one NO2, and one SO4. And I know that might be a little bit unconventional keeping those together, but I promise you, it makes this a whole lot less confusing when you're able to keep those polyatomics together and just balance them whole as opposed to balancing each atom. All right. So what do you want to start with? You want to start with the sodium or you want to start with the hydrogens? It's your choice.
Hydrogen.
Hydrogen. So we want to balance that first. So what would you do? What would you do to balance?
Use 2 as the coefficient.
We'll put a coefficient of 2 in here. All right. So now we got, this would be two hydrogens. And then we're also going to change the number of NO2 molecules. So you got two of those. Is that right? And now let's balance the, so if we balance the NO2s, can you see right away that we're also going to balance the sodiums as well? Because if we, once we balance the NO2, which we'll use another coefficient of 2, then the sodiums are also going to be balanced at the same time because you got two sodiums on each side, two sodiums on the other side. Can y'all see that right here?
Yes, sir.
So if I put a 2 here, that's going to balance it's going to give me two sodiums and then two NO2s. So you can see now everything is balanced. You got two hydrogens, two sodiums, one sulfate, and then two NO2. So that's fully balanced. All right. And it's important to understand again when to recognize keeping those polyatomics together. And in this case, if you can see them on both sides intact, then you go ahead and you can balance them by keeping them together. Let me put that in as a note down here. Because we talked about it on Thursday, but and that's just kind of I don't like to call it a shortcut, but it's a way to kind of shorten down that process. All right. All right, let's look at the next one. We have CO2 plus water going to C6H12O6 plus oxygen. All right. So now this we're going to have to balance atom by atom because there's nothing we can keep intact, right? Everything is, combined on the other side, right? So you got new compounds. So let's balance carbon, oxygen, and hydrogen. So for carbon, we got one carbon, three oxygens, and two hydrogens. Over here, we have on the product side, remember this is the reactant side. And then this is the product side, always left to right. So this is what, 6 carbons, 12 hydrogens. Let me keep them in order though. 8 oxygens. And then 12 hydrogens. All right. Let's start out by trying to balance the hydrogens. Let's start there. Right, because I think that might make it easier. So let's do this. Let's put a 6 here. That's going to give us 12 hydrogens, and it's also going to give us so this is going to be 6 plus 2, 8 oxygens. Following? Because this is going to make that 6 oxygens plus these 2 right here. So it's going to be 8 oxygens total on that side. We're going to have to do something else though, because we're going to have to balance the other side as well, because that's going to screw up the count when we balance the carbons. So let's think about that. How do we want to balance the carbons in light of, because right now the hydrogens and the oxygens are balanced, but the carbons are not. So that's going to really jack us up. But we could probably fix it. So let's see what we can do. what do we want to do with the I'll see it. What do we want to do with the carbons? How are we going to balance that?
By 6.
Put a 6 here. Is that right? So that's going to be times 6. And then that's going to give us 12 oxygens there, right? And then, so now it's going to be 12 plus 6. So I'm going to just edit this instead of rewriting it. But is everybody okay with that? This is going to give me 12 oxygens. This is going to be 6 times 2. And then we have 6 based on this balanced water right here. So now we're going to have 18 oxygens. Is that right?
Yes, sir.
All right. I see it. Can you see what we need to do now? How can we get that other side up to 18 if we have 8?
Increase the oxygens by shit.
By 10 or by 12? We could go up by 20. We need to go up. We got 6 and 2, so that's 8 total. And we need to get to 18, so we need to go up by 10, don't we?
Yeah, so bring the O2 up by 5. Wait, hold on.
Well, no, that'll only give us 16. But if we go up by go up 6,
yeah, by 6.
then that'll give us 18. Good. So we're gonna put a 6 right here. So yeah. And so a lot of times you can kind of, once you start putting the coefficients in, you can see the light at the end of the tunnel. So if we put a 6 here, that's going to make that 12. So our oxygens are going to go up. And it's very important to keep track of these numbers because it's easy to get lost in the sauce with this balancing. So that's going to be 12 plus 6, which will give us 18. Anybody not following that one or have a problem with it? So now it's balanced, right? We got 6 carbons on both sides. We got 18 oxygens on both sides. And we got 12 hydrogens on both sides. All right, let's do another word problem where we got to kind of go from scratch. Any questions about that before we move on to another problem?
Yeah, would it be but would it be possible to like, so we have the oxygens, could we have written it like C, then O, then like O2, and then H?
That's a good, you mean break it apart like that and balance it that way?
Yes.
If that works for you, by all means, you could have done that. So you want to do oxygens and then O2 by itself, or you want to combine the oxygens on the right side? Is that what you're saying?
No, I was gonna break them up.
Yeah, you could do that. It may be a little bit more cumbersome for somebody else, but if that's how you're able to visualize it, then by all means do it. Did you come to the same conclusion?
Oh no, I was just thinking that like after
Okay.
I kind of wrote everything out.
Okay, yeah. You can write it out like that if you chose to. I just think it's this way seems a little bit more compact and a little bit more efficient. But by all means, if you could try that and see if you get to the same answer, and if you do, you know, that may be more comfortable for you to do it that way. And I don't have a problem with that as long as we get to the same place.
Okay, thank you.
All right. Let's do another word problem. Let's do this one. It says copper, and then I'm gonna introduce you to a couple of other things, and then we'll pick up on Wednesday. So it says copper and sulfuric acid react to form copper 2 sulfate, water, and sulfur dioxide. So we're going, this is a lot because it's actually touching on a bunch of different topics that we haven't touched yet, but we will. Right, so you got copper, which we can write as simply Cu. Didn't say if it was copper 2 ion or copper 1 ion. So when it doesn't say that, you assume it to be the neutral atom, which is just Cu with a charge of 0. So we want to react that with sulfuric acid, which looks like this, H2SO4. And this is something that you can commit to memory. It doesn't change, right? Sulfuric acid is always the same as H2SO4. All right, so we're going to react those two together. And let me fix my U. Kind of looks like an N. All right, we're going to react those two together to give copper 2 sulfate. So CuSO4. How do I know that it's just CuSO4 and not something else? How do I know to put that together like that? What's the, I guess the point I'm getting at is, what is the charge on the sulfate anion? Somebody help me. It's a polyatomic. We learned it back in the day, which was a few weeks ago. And it has a specific charge. And the name also helps us understand that too. In other words, how if I blew that up, pulled it apart, what would it look like? What would the charges be on copper, and what would the charge? What's the charge on copper? Let's think about that. Based on the name that's given, the stock name with the Roman numerals.
2.
Good. So this, if we were to blow this up and show the pieces, the ions that came together, it would be what? Cu2 plus. And the fact that there's no subscript here outside the sulfate anion, this must have the exact same charge as copper when you put them together. And the sulfate anion has a -2 charge, by the way. All right, so keep refreshing those. Don't forget about the polyatomics, because you're going to see them in perpetuity from this point forward. So if you need to go back and look at them, kind of glance over them a little bit, do it. Don't feel like just because we passed that part that you don't need it anymore, because you're going to need it going forward. So go back and refresh yourself on those. All right, so that's that. And then plus water and SO2.
Dr. Russell,
Go ahead.
I don't know how to get the charges for like the transition metals. Because isn't copper a transition metal?
Yes, it is. And it's based on really the transition metals. Some of them have like multiple charges. But in that group with copper, if I'm not mistaken, the main charge is, it can be copper can be the +1 or +2. But I think the other elements in that row are +2.
So it's more like naming to get because like you said, with the Roman
The
numerals.
Roman numeral
that
tells
go,
us,
right.
yes, which oxidation state copper is in, because they can all have, well, not all, but a lot of the transition metals have multiple oxidation states they can reach.
Okay.
Yeah. So just look out. If you have a name like that, make sure you pay attention to if there's a Roman numeral present. Otherwise, you can infer the charge based on the charge of the anion, which is the sulfate. If you know that's -2, then you can kind of, if you know there's no Roman numeral, then you can also infer that the charge is something different. All right. So
Okay. Thank you.
yeah. Good question. That's a good question. All right. So we need to balance this out. So in this case, because the SO2 is there, I don't want to keep the the polyatomics together, because you got two different polyatomics on the other side. They both contain sulfur. So in this case, it's going to be better to just balance each atom. Are y'all following that? Do you see the nuance there? In the previous example, we had both the polyatomics were intact on both sides, no problem. Here, you have that SO2 molecule over there, but you also have an SO4. So now you got a problem, right? Because if you keep the polyatomics together, how do you balance SO2 on the left side? You can't. You don't see it on both sides. So in this case, we're going to actually balance, do an atom for atom balance. So this is going to be copper. And then let's do hydrogen, sulfur, oxygen. And then we'll do the same thing over here. Copper, hydrogen, sulfur, oxygen. Are y'all understanding the method that I'm talking about instead of keeping the polyatomics together? Because you can't see them on both sides. There's no SO2 on the reactant side, right? So because of that, we're going to balance it atom for atom instead of using the other method by keeping the polyatomics together.
Right. Isn't that single displacement or something?
This reaction, yeah, I guess you could think about it like a single displacement because you only swapped out the sulfate with the hydrogen. But the point I'm making is that the fact that you don't have a SO2 on the reactant side,
Okay.
it kind of screws up the other method where you can keep the polyatomics together. So we're going to balance it just by the atoms. So we got 1 copper, 2 hydrogens, 1 sulfur, 4 oxygens. And over here, we have 1 copper, we have 2 hydrogens, we have 2 sulfurs, and we have how many oxygens? 4, 5, 7 oxygens. This is going to be ugly. All right, so we got 7 oxygens. That's 2, 3, and 4. That's 7. 1 copper, 2 hydrogens, and 2 sulfurs. What do you want to try to balance first? Because everything is balanced except for the sulfurs and the oxygens. So you want to try to balance the sulfur first or the oxygen first.
Do sulfur.
All right, let's try that. So let's see what happens if we put a 2 here. All right, so if we put a 2 here, and we may have to go back and revise this, right? The 2 might not be the right coefficient, but right now we're trying to get 2 sulfurs on both sides. So that's going to give us, this is going to be 4 hydrogens. It's going to also increase the number of sulfurs to 2. And it's going to increase the number of oxygens to 8. All right. So on the other side, now we got 2 hydrogens. We got 2 sulfurs, 1 copper, 7 oxygens. So now let's see what happens if we try to balance the hydrogens, because that's going to touch oxygen in a different way. And it may, let's see, it may help us. So we got how many? 4. So let's put it, if we put a 2 here, that's going to be 4 hydrogens. And then for oxygen, it's going to be 4 plus 2. Okay, God. Plus what? Plus 2? Is that right?
Yes.
So oxygen now is going to be what? 8. That's I thought this was going to be ugly, and it ended up not being ugly at all. Is that balanced? That's balanced, isn't it?
Yeah.
Look at God on a Monday. One copper, 4 hydrogens, 2 sulfurs, and 8 oxygens. Ain't that something? I thought for sure this was gonna be really, really difficult with that odd number of oxygens, but sometimes you can psych yourself out, and that's bad. But this is okay. So we see now again, even though we didn't keep the polyatomics together, we still were only dealing with 4 atoms, right? Copper, hydrogen, sulfur, and oxygen. So this is again, balancing is an art. It's an art. So sometimes you may apply the method where you keep your polyatomics together. Other times you balance it atom by atom. It's case by case. There's no one stop shop, but there are some steps that are going to be the same no matter what you do. And that's going to be to write out the atoms, right? You got to do that. You got to take an inventory of what you have, figure out how much of each atom is present, and then you go about adding in your coefficients. So those 3 steps are always going to be the same, but it's the way that you apply that method that may change. All right. Any other questions about that problem or the one we did before? All right, these are actually some good examples because it kind of gives us some information necessary to move forward with some of these other reactions. And we're going to look at now looking at some different ways to write chemical equations because and we're going to keep balancing. Everything from this point forward is going to require us to be able to balance equations. So we're not moving away from balancing. We're just going to be applying it to the problems that we do going forward, right? So we're still going to be balancing equations no matter what. Let me just leave that and then move this. Add a page. All right, so we're going to talk now about some different types of equations. And we're going to talk about how to write like what we call the net ionic equation. That's the next step in the progression. Let me see what section this was. So I think I put that up here. And the introduction. All right, so we're still dealing with writing and balancing equations, so section A. But this is just another topic. Right, so when we write a net ionic equation, what we're normally talking about in this case is some reaction happening in aqueous media, where you have to dissolve up your reactants. And aqueous is just a cute word for water. So if you're dissolving everything in water. So you dissolve all your stuff up in water. And a lot of times when you dissolve up metals, or you dissolve up, compounds that contain metals that are ionic, where you have compounds of a metal and a non-metal coming together in an ionic fashion. When you dissolve those things up, they actually dissociate. Right. So if I were to take like calcium chloride and dissolve that up in water, right, it would actually dissociate into ions. Right, so it'll dissociate into ions. So a lot of times what happens is when you have a specific type of equation or a specific type of reaction that's happening and is in aqueous solution, you can break those apart. And what you'll find out is that some of the ions are the same in both the reactants and the products. And those are what we call spectators, and you can get rid of them. So let's take an example. And we'll point out all of the stuff I just mentioned, spectators and all that stuff. So let's take an example. Let's take calcium chloride. Right, and we're going to react that with silver nitrate. And this will also give me a chance to introduce another piece to this, which is dealing with precipitates and solubility. So I have a calcium chloride and silver nitrate, and I'm reacting those two together. And this is, I think Saxton mentioned this earlier, well, a version of it. This is what we call a double displacement, right? So we're going to swap partners. That's all that means. It's a complex phrase, but it just means we're swapping partners. So the cation, right? This is our cation, because it's calcium 2+, and this is our anion, right? It's Cl-. It's going to, so the cations are going to swap with each other, and the anions are going to swap with each other. So same here, metal, non-metal. So this is silver is our cation, it's Ag +1, and then this NO3 -1. So this is cation and anion, and they're just going to swap places, right? So where you see calcium, you're going to have silver. Where you see silver, you're going to have calcium. So let's write out the double displacement, right? So silver, now this is going to become what? Silver chloride, which is insoluble, by the way. And it's going to precipitate out, but we're going to talk more about precipitation reactions a little bit later. But you can see on the chart that I moved and shouldn't have that silver is going to form a precipitate if it's paired up with chlorine. I actually wrote a little rhyme about this. I'm going to turn it into a video poster because it'll help you to remember, because this is a lot. These solubility rules that's a lot to remember. But I think if you put it to music, it'll click. So I may work on that today at some point. I got the beat in my head. I got the words written out. I just got to put it together. So yeah. All right, so that's that. And then over on the other side, you're going to get silver chloride, right? Ag+. And then, so you can see now this is again, this is a cation, this is an anion. And then plus what? What's the other part? Right, so this is calcium. And then calcium is group 2. And this is calcium nitrate. Is that right? With a 2 here. Everybody following that? If calcium has a +2 charge and my polyatomic nitrate has a -1 charge, you can see that right here. When you put those together, let me just write it out. This is going to be Ca2+ and then 2 NO3-, right? So when you crisscross those charges, well, let me not put the 2 there yet. When you crisscross the charges, you see what you're going to get there, right? So if I put this charge here and then take the -1 and put it here, there's understood to be a 1 there. So that's the point I'm trying to make. So we got to remember those polyatomics. We can't forget them. Can't move away from them. But when I break this apart, I'm going to take that 2 and put it here. All right. So what I've done actually is in the top, this is the molecular equation. Right. And by writing out the ions, I've actually written out what's called the Ionic equation. So it's this. All right, this is what we call the ion. This is where I take all the ions and I break them apart. And I'm gonna show you a couple of things to remember here. Right, if you notice, there's a 2 here. So when I break this apart, I need to keep that 2 in front of chlorine. Whatever that subscript is on that anion, I'm gonna put it there. Right, and first let's make sure this is balanced, because right now it is not. All right, so let's balance this. So we have 2 chlorines over here, so we're gonna need 2 here to balance that. And then we need to balance the silver, so we need to put a 2 here. Anybody not seeing the balancing part? So now that's 2 silvers, 2 nitrates. We got 2 nitrates on the other side, and then 2 silvers and 2 chlorines, and then 2 chlorines on the reactant side. So that is balanced. All right, so what we need to do now is take the coefficients and make sure that we got them in the Ionic equation as well. So this is, that's a 2 there. We're gonna put a 2 here. And on the other side, we got 2 Ag plus, and then plus 2. Actually, you know what? We're gonna leave this because it's a solid. It's not in solution. So we can't say that it's dissociated. So we'll leave that. Plus Ca2 plus and 2NO3 minus. So that's our total like ionic equation. Right. So everything you can see now, what you notice is that you see some things that are the same on both sides. Right. So the calcium 2 plus is the same on both sides. The nitrate is the same on both sides. And the same coefficient, everything, right? So these are what we call spectators. Right, so we have the molecular equation, which we balanced. We have the ionic equation, which we break apart based on what the molecular equation is. And now in the ionic equation, we see that we have what we call some spectator ions, right? They are present on both sides of the equation. So let me put that in here as the definition. All right, so they're present on both sides. So we can actually get rid of those and write what's called the net ionic equation. So this is the overall equation. What would it be? Based if we took the spectators out. So I'm just going to line through these here, 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 here. What's left is what we call the net ionic equation. So you're going to have basically 2 Ag plus 2 Cl minus going to, I left my 2 off here. Sorry, there should be a 2 there. 2 AgCl. And because all the coefficients are the same, we can just reduce them down. So this is just going to be Ag plus Cl minus going to AgCl. So this is the net. So you have the molecular equation where you just write out the compounds as they are and then balance that. And then you have your ionic equation where you pull up compounds apart that are still in solution. And then with the net ionic equation, you get rid of your spectator ions and then you're left with the overall. That's why it's called the net. It's what's left over after you get rid of the spectators. All right, questions about that? Right, so for when you see an equation and it talks about this compound plus this compound were dissolved in water, that's how you know that you can do an ionic equation, because this is dealing with solutions and compounds that are dissolved up in solution. All right, so anytime you see that word dissolved, that's a key word for this type of process. So when you see that word dissolved, what that means is that the ions that make up those compounds are going to what we call dissociate, or they're going to come apart. And that's how they're able to interact with other ions and do double displacement. They dissociate, then they start bumping into other ions that have dissociated, and that's how the reactions happen. All right, any questions about that? All right, if not, we're going to actually stop here because we only got 2 minutes left, and I want to do another example, but I don't want to start it and then go over time. So we're going to work on this today. Wednesday, we're going to talk about solubility, and we're still going to be balancing. So don't worry about getting out of habit with that. We're going to balance. Everything is going to require some balancing. So Wednesday, we're going to talk about solubility, and Thursday, we're going to work through some more problems of these types. And then we're going to also do redox reactions, which are coming up as well. So we'll have a bunch of stuff that we got to finish, but we'll get to it. All right. Any questions about anything? All right. I'll see y'all on Wednesday, God willing. Have a great day. And I'll post the notes and the recording to Blackboard shortly.
Thank you. Have a good one.
All right. Y'all take care.
Have a nice day.
All right.